মানে আপনি শেয়ার করতে হবে। বলছি যে এটা তো আপনি সাড়ে দশটার পরে বলবো ওনাকে ফোন করে যদি বলে কিছু লাগবে না গাড়ি করে দেবো, যদি কিছু লাগবে ওনাকে জানিয়ে 5:50 শুরুয়ে ঢোকার আগে অল্টারনেট ক্লিয়ার করে দেবো প্রোগ্রাম। আর তারপরে ছবি, কারণ আমি তো 5:30 আগে বেরোবো, ঠিক আছে? Okay, good afternoon, all of you. Today is our second and final session of waves. The second and the concluding session of waves. Today we will be completing waves, the whole chapter, whatever is left of it. So I'll just quickly remind you that in previous sessions we have already done Doppler effect of sound. That topic is over. We have done mechanical waves on a string. That topic is also over. And now and of course when we were doing mechanical waves on a string, there was a topic standing waves, and while doing standing waves we have also discussed standing waves in an open air column or a closed air column. So now in this chapter what is left for us is to discuss the equation of sound waves, the speed of sound waves, the loudness intensity of sound waves, superposition of sound waves. And so if we do that, this chapter will be over, waves will be over. So let's begin the session by discussing the wave equation of sound waves. Like sound waves are waves, so they will definitely have a wave equation. So let's begin the class with that. So as you know very well that sound waves in air are basically longitudinal waves, and just a quick understanding what exactly happens during the propagation of sound waves, a very quick understanding. So a quick understanding of what happens during propagation of sound waves. So this is layers of air, like these are the layers of air, they are spaced out when the air is in equilibrium, like there is no disturbance. Like suppose imagine that there is a room in which there is no sound at all, so the air layers will be spaced out equally like this. Now suppose there is a sound, let's say there is a sound. So if there is a sound, then what will happen? The air layers will either come very close or they will spread very far apart. So when the air layers come very very close to each other like this, when they come extremely close to each other, so that situation is called a compression. And when the air layers are totally spread out, okay, so when the air layers come very very close to each other, that is called a compression. And when the air layers are completely spread out, that is called a rarefaction. And in fact, just like transverse waves have crests and troughs, like every transverse wave has a amplitude maximum which is called a crest, and amplitude minimum which is called a trough. So similarly, longitudinal waves, they propagate by alternate. Okay, so the thing is that just like transverse wave propagate by alternate crests and troughs, so longitudinal waves propagate by alternate compressions and rarefactions. So compressions are regions of the air layers become very close to each other, so the positioning between the air layers is minimum distance between them. And rarefaction is just the opposite, the air layers are totally spread out. So in a compression the air layers are all packed together, in a rarefaction they are totally spread out. And alternate compression and rarefaction makes up the manner of propagation of longitudinal waves or sound waves in air. So this compression, rarefaction, it keeps happening alternately, and that is how sound waves propagate in air. So So that is how sound waves propagate in air. So that means if I want to describe the equation of sound wave, then to describe the equation of sound wave, I can describe it in terms of the displacement, I can describe it in terms of the pressure. So I think it is fair to expect that compression will be high pressure, right? Because the air layers are very close. So compression will be the region of high pressure and rarefaction will be the region of low pressure because the air layers are spread out. So compression is high pressure, rarefaction is low pressure. So when we are wanting to write the equation of a sound wave, so we will have to make a choice. Do we want to write the equation in terms of displacement or do we want to write the equation in terms of pressure? So suppose I have decided in my mind, let's say I have decided in my mind that I want to write the equation of sound wave in terms of displacement. So S equal to S0 sine omega into t minus x by v. This will be the equation of sound wave in terms of displacement. How are we getting this? Actually, S0 is the displacement amplitude, right? That is the maximum displacement from the undisturbed position of the air. And sine omega, you are aware omega is angular frequency, v is the speed of the sound or speed of sound wave. You can call it speed of sound, you can call it speed of sound wave, it's the same thing. So this is the displacement equation of sound wave, and usually this equation is used when we are interested in the the displacement rather than whether it is high pressure or low pressure, but we may be interested in describing the wave equation in terms of pressure also. So in terms of pressure, the formula is P equal to P0 cos omega into T minus x by V. So when you say displacement, it is S0 sin omega into T minus x by V, and when you say pressure, P equal to P0 cos omega into T minus x by V. So this pressure equation, it has also got a pressure amplitude. So in the pressure equation also there is one term P0, that is for pressure amplitude, and cos omega, again angular frequency, T minus x by V. Now why is it that the displacement equation is a sine function and pressure equation is a cos function? That means they have complementary relation. What is the significance of that? See, when the displacement will be low, that means the layers will be very close to each other, like here, that time the pressure will be high, so that is a compression. And when the displacement will be maximum, that means the air layers will be totally spread out, so that time it will be a low pressure, that is rarefaction. So displacement minimum means pressure maximum, displacement maximum means pressure minimum. So displacement and pressure have a complementary relation. When one of them is the highest, the other is the lowest, and that is why this is sine and this is cos. So the reason why displacement is sine and pressure is cos, because they have a complementary relation. When this is maximum, this is minimum, and vice versa. Another thing, that the pressure amplitude P0 is related to displacement amplitude by one formula. The formula is P0 equal to bulk modulus of the medium B into S0. S0 is the displacement amplitude into omega by V. So P0 is B into S0 into omega by V. So this is the equation which gives the relation of pressure amplitude in terms of displacement amplitude. Okay, so these are the basic concepts of displacement equation and pressure equation of a sound wave. Okay, just to get a better idea of so just to get a better idea of displacement and pressure. So have a look at this diagram. So there are two loudspeakers facing each other. Okay, have a look at this diagram. There are two loudspeakers facing each other, and there is a person in the middle. Okay, there are two loudspeakers facing each other, and there is a person in the middle. He is listening to the sound of both the loudspeakers, right? So when this person is listening to the sound of both the loudspeakers, the displacement of the air thanks to this loudspeaker will cancel the displacement of the air thanks to this loudspeaker. So the displacements of the air thanks to both the loudspeakers will cancel out at the place where the person is standing. So at the place where the person is standing, assuming that he is standing midway between the two loudspeakers, the displacement will cancel out. So the displacement due to this and displacement due to this will cancel out at the place where the man is standing. But where the place where he is standing, he will hear the full amount of sound from this loudspeaker and this loudspeaker both. So the pressure will be maximum. So the displacement of the air layers over here will be zero, because he is standing midway and there are two loudspeakers of equal intensity. So the displacement of the air layers will cancel out at the point where he is standing. But the pressure will be maximum because of the fact that he is getting to hear the sound of both the loudspeakers. So this is an example that displacement and pressure have a complementary relation. When one is maximum, the other is minimum. Okay, so suppose you have these three formulas. Okay, the speed of sound in different mediums. So speed of sound in different mediums. First is speed of sound in solids. So speed of sound in solids will be root over of, first of all, let me clarify something to you. The speed of sound is directly proportional to the square root of elasticity and inversely proportional to square root of density. Okay, that is an important factor. So the speed of sound, it will be proportional to the square root of elasticity and inversely proportional to square root of density. So suppose if you are talking about solids, so in solids, elasticity means we are talking about Young's modulus. So it will be proportional to root over of Young's modulus divided by density. And the same type of formula is for liquids and gases. In case of liquids, instead of Young's modulus, we use bulk modulus. In case of gases, Sir Isaac Newton had suggested that the propagation of sound is an isothermal process, and he had suggested, just like here is Young's modulus and bulk modulus, he suggested here we should take pressure, and his logic was that propagation of sound is isothermal. But later there was another scientist called Laplace, and he proved that propagation of sound is an adiabatic process. So instead of pressure, it became adiabatic exponent into pressure. So in solids it is root over Young's modulus by density, in liquids it is root over bulk modulus by density, and in gases it is root over of gamma into pressure by density. So gamma is adiabatic exponent into pressure by density. So these are the formulas of speed of sound in solids, liquids and gases. Now, these three formulas, the speed of sound in solids, liquids and gases, these three formulas, what do we learn from these three formulas? That the speed of sound will increase if the elasticity is more. So I think you all are aware that solids have very good elasticity, liquids is much lesser, and gases have virtually no elasticity at all. So if elasticity is more, speed of sound will be more. So that means solids, they should have the highest speed of sound, and it is inversely proportional to square root of density. Now solids have very high density, so that means the speed should be less. Liquids have lesser, and gases have the least density. Now both are opposite effects. Elasticity increases the speed of sound and density decreases the speed of sound. But by calculation, it was found that the speed of sound is much greater in solids than liquids than in gases. Just to give you a relative comparison, let us take steel, water and air, like normal air, which the air we breathe in, all around us the air, which is a mixture of several gases. So if you consider the speed of sound, so for steel it's around 5100 meter per second, then for water it's around 1400 meter per second, and for air it's around 330 meter per second. So the speed of sound in steel is 5100 meter per second, water is 1400 meter per second, air is 330 meter per second. So you can see that the speed of sound is considerably more in solid than liquid, and obviously gas is the least. So the effect of elasticity is much greater, right? The other thing is that the gases one, there is one assumption which I think we are kind of used to, that is we are assuming ideal gas. So this gamma p by density is applicable only for ideal gas. So that's kind of something which we have got used to. We all the time assume kinetic theory before doing any question. So if it is an ideal gas, then instead of pressure by density, you can also write RT by M. So since it is an ideal gas, you can replace pressure by density with RT by molar mass. So instead of writing gamma into pressure by density, you can write gamma into RT by molar mass. You can do that. Now, if you have a look at these two formulas for speed of sound in gas, what are the conclusions we can derive? First of all, the speed of sound will increase if the density is less. We are only talking about gases now, only air, gases, whatever. So if the density is less, the speed will be more. So that is point number one, because density is in the denominator. So if density is less, speed will be more. Number two, humidity. Humid air is less dense than dry air. Okay, the density of humid air is lesser than that of dry air. So if you have humid air, the density will be less. So automatically the speed will be more. So in humid air, the speed will be more. That is number two. Number three, you can see that in this formula it is proportional to square root of temperature. Temperature of course means Kelvin temperature. So this is number three, that if the temperature is more, the speed of sound will be more, because it is proportional to square root of temperature. Number four, if there is any wind blowing and if the wind is assisting the sound, the speed will be more. But if the wind is blowing opposite to the sound, speed will be less. So if wind is assisting the sound in its motion, the speed will be more, but if wind is going the other way, the speed will be less. And one interesting thing is that in the formula, the pressure term is there in the numerator, but change of pressure does not change the speed of sound. Why does that happen? The reason is that pressure and density go hand in hand. So if you alter the pressure, the density will also alter itself, and therefore, because it's a gas, and therefore pressure alteration does not affect speed of sound. So this is the topic, speed of sound, and the factors
which affects speed of sound in air. Okay, um, there's this topic called loudness and intensity. See, the moment we hear the word sound, okay, the moment we hear the word sound, the first thing that we try to associate with sound is loudness. That is a very normal, natural response. The moment you hear the word sound, you try to associate it with loudness. So basically, what happens is that there is a source of sound. Okay, there is a source of sound, and sound is coming out from this source, and the sound is traveling in the form of a longitudinal wave. And you imagine that there is a square of 1 meter by 1 meter dimension. Suppose there is a square whose dimension is 1 meter by 1 meter, and this square is placed in the path of the sound wave. Okay, there is a square of 1 meter by 1 meter, and the square is placed in the path of the sound wave, and the square is placed perpendicular to the propagation of sound wave. Like whatever is the propagation of sound wave, the square is perpendicular to that. So you understand that sound energy, sound is a form of energy. So the energy that is passing through this 1 meter by 1 meter area per unit time, okay, the average energy that is passing through this 1 meter by 1 meter area per unit time, that is known as intensity. Now, why am I using the word average energy? The reason is that you understand that whether you take pressure equation or displacement equation, so it's a variable thing, it's a wave. So that's why in one time period, whatever is the energy passes, that divided by the time period, right? That means you know that it is a sine or a cosine function. So therefore, the amount of energy that passes in one time period divided by the time period, so that is energy per second, and passing through a 1 meter by 1 meter square placed perpendicular to the propagation. So that is called intensity of sound. In fact, intensity of sound has got a formula. Okay, in fact, intensity of sound has got a formula. So you can write P0 square into velocity by 2 into bulk modulus. Or you can do one thing, you can just write P0 square by 2 into density into velocity. So either you can write P0 square into velocity by 2 into bulk modulus, or you can write P0 square by 2 into density into velocity. So either of these two formulas you can use for intensity of sound. This is a formula, but otherwise the definition of intensity is it is the energy passing through a unit square placed perpendicular to the direction of propagation per second, and the average such energy, right? So that is called intensity of sound. So intensity of sound, if it is high, that means the sound will be loud, and if intensity of sound is low, that means the sound will not be very loud. The other thing is that intensity is having a factor P0 square. So intensity is proportional to square of amplitude. This is also an important thing we can derive from this formula. Intensity is proportional to P0 square, that means square of amplitude. now we come to uh, the fact that um, is intensity a worthwhile pursuit? I mean, is it worthwhile going after intensity, measuring intensity, and is it really a very helpful calculation? The truth is that normal conversation or normal sounds, unless they are very loud and explosive, they are in the intensity range of 10 to the power minus 12 watts per meter square. So you can see that it's a really, really low value. 10 to the power minus 12 watt per meter square means it's really, really low. So this intensity is so low that the scientists unanimously decided that it is not worthwhile pursuing intensity, and we should have a better measurement of sound for day-to-day assessment. So then they decided that for day-to-day assessment they will use something called decibel, and the symbol the symbol for decibel is beta. Okay, the symbol for decibel is beta. So 10 log I by I0 to the base 10. So what you need to do is, the sound whose loudness you want to measure, suppose the intensity is I. Okay, there is a particular sound and you are keen on measuring the intensity or loudness of that sound. So suppose that is I. So you just do I by I0, and I0 is 10 to the power minus 12, by the way. So I by I0 take log to the base 10. Whatever you get, multiply that with 10. This will be the answer in decibel. Okay, so decibel is the better measurement of loudness. Now, why is decibel considered better than intensity? What is the reason? So, okay, now just to give you an idea why decibel is a better marker than intensity. So if a person is talking in a whispering voice, then the decibel value is 10. So if a person is talking in a whispering tone, then it will be 10 decibel. Suppose if two people are having a normal conversation, then it will be 60 decibel. Like normal conversation where nobody is shouting or screaming, they can hear each other clearly. So that is 60 decibel. Suppose you are standing just below an aircraft which is about to take off, then the sound that will be heard will be beyond 120 decibel, and it could even go up to 140 decibel, which is enough to shatter the eardrums. So if sound goes excessively high beyond 120, that is definitely going to damage the eardrums of that person. So whispering voice is 10 decibel, conversation 60 decibel, and if a plane is about to take off, then it will be more than 120 decibel. And more than 120 decibel could go up to 140, so that is definitely harmful for the eardrum. So overall, you can see the range is a very reasonable range. So instead of absurd values like 10 to the power minus 12, you have reasonable values like 10, 60, 120, which are easier to handle. Okay, now we come to a very important topic, which is a continuation, you can say, of the superposition principle, which we have already done. Uh, we have already discussed superposition principle in case of mechanical waves on a string. So, superposition of sound waves. So, let us have a quick recap that what exactly is superposition. So, you are aware that whenever two particles meet each other, that is called a collision. But when two waves meet each other, then what happens is that uh, they lose their identity and create a new wave. And this phenomenon is called interference. And the concept by which we find the new wave, that is called principle of superposition. But remember, there is a condition that interference will happen only if the phase difference between them is constant. So you know that there will be two waves, and if the phase difference between them is constant, then only interference will happen, and then only by principle of superposition you will get a resultant wave. If the phase difference between them is not a constant, then in that case you will not have interference. In that case, what will happen is that the two waves they will approach each other, and after passing through each other they will just continue their passage as if nothing has happened. So there will be no observable phenomenon due to the meeting of the two waves. But if they are coherent sources, that means if the phase difference between them is a constant, like here the phase difference is delta. So if the phase difference is a constant, then only they will interfere and they will produce a new wave by principle of superposition. So let us consider two waves. The first one is P1 equal to P01 sine kx minus omega t. The second one is P2 equal to P02 sine k into x plus delta x minus omega t. So that is P02 sine kx minus omega t plus k delta x. Now the thing is that these are the two waves, and k delta x is the phase difference between them. Okay, k into delta x is the phase difference between them. Let us denote it by this symbol delta. So delta is k into delta x. So k will be the wave number, as we know, and wave number is 2 pi divided by wavelength, that is a formula. So delta is the phase difference, that is k into delta x, that is 2 pi by wavelength into delta x. And what is this delta x? What is this? This is the path difference. So the two waves have a path difference delta x, due to which they have a phase difference delta, and the relation between delta and delta x is given by this equation. So when these two waves interfere with each other, they will create a new wave, P equal to P0 sine kx minus omega t plus epsilon. So this is the phase epsilon. So in this equation, P0 is root over P01 square plus P02 square plus 2 P01 P02 cos delta. So this is the resultant amplitude P0, root over P01 square plus P02 square plus 2 P01 P02 cos delta. And this epsilon is given by the formula tan epsilon is P02 sin delta by P01 plus P02 cos delta. So this is tan epsilon, okay, and this is P0 and this is the new wave. Once again, let's try to recall that when two waves interfere, then you will have a maximum possible amplitude and a minimum amplitude. So that is called respectively constructive interference and destructive interference. So constructive interference, delta is equal to 2n pi. Okay, so that means the phase difference between them is going to be an integer multiple of 360, that is 2 pi. And you can see that cos of any multiple of 2 pi will be 1, so that is the maximum. So delta is 2n pi and delta x is n lambda. So the phase difference is multiple of 2 pi, so 2n pi, and path difference is n into lambda. So this is the phase difference and this is the path difference between them. And how did we get the path difference? This 2n pi if you put here, then automatically delta x will be n lambda. What about destructive interference? Destructive interference means that the cos value will be -1 that is the lowest possible value of cos. So that happens when cos is multiple of 360 plus pi. So delta is 2n plus 1 pi. So if you replace delta as 2n plus 1 pi, delta x will be n plus half lambda. So this will be the combination of delta and delta x for constructive interference, and this will be the combination of delta and delta x for destructive interference. And constructive interference, P will be P01 plus P02. So P will be P01 plus P02. This is in case of constructive interference, and P equal to P01 minus P02 modulus. That means it's either P01 minus P02 or P02 minus P01. So this will be for destructive interference. So constructive interference, you have to add the two amplitudes, and destructive interference, you have to take the difference of the two amplitudes. So this is the topic, constructive and destructive interference. So suppose you have two sound waves whose equations are P1 is P0 sine omega 1 into t minus x by v, P2 is P0 sine omega 2 into t minus x by v. Suppose there are two sound waves, the first one is this and the second one is this, and you want to find the resultant of these two. So So P1 plus P2, it is P0 into sine omega 1 into t minus x by v plus sine omega 2 into t minus x by v. So what you do is, this is sine C plus sine D. So 2 cos 2 sine C plus D by 2 and cos C minus D by 2. So there is a cos term and there is a sine term. Okay. Now what we normally do is that So what we normally do is that we take this entire expression from here to here, this entire expression we take it as capital A. So this expression is symbolic of the amplitude, so we take it as capital A. Sine, and this omega 1 plus omega 2 by 2 we take it as omega. So A sine omega into t minus x by v. So this whole thing is symbolic of capital A, sine, and then this is omega into t minus x by v. So this is the resultant wave due to the superposition of these two waves. Now this resultant wave, what we can see is that the amplitude of this resultant wave is not a constant. The amplitude is having a term cos omega 1 minus omega 2 by 2 into t minus x by v. So that means the amplitude is not a constant, it is variable. So according to scientists, the suggestion given by them was that the amplitude is cos omega 1 minus omega 2 by 2 into t minus x by v. It depends on a cosine function of time. So according to the scientists, they said that when you have a positive amplitude maximum and a negative amplitude maximum, right? You understand that this amplitude term, it will have a positive maximum and a negative maximum. So the positive maximum and negative maximum, between them, the frequency of change, it will be double of this, because positive maximum and negative maximum. So omega 1 minus omega 2 by 2, okay, that you can say will be for 0 to positive amplitude maximum, and same thing from 0 to negative amplitude maximum. So that means the amplitude is changing with the frequency omega 1 minus omega 2, that is double of this. So So the amplitude is changing with the frequency modulus of omega 1 minus omega 2. This is called beat frequency. So the change of amplitude is happening with this frequency, and it is known as beat frequency. So beat frequency is the frequency at which the amplitude is changing, right? And what we normally do is that when we are doing any measurements, it is usually velocity, frequency, wavelength. We normally don't relate to this angular frequency. So that is why the correct definition of frequency, beat frequency, is modulus of f1 minus f2. Why do we put a modulus? Because beat frequency is a positive quantity. So if f1 is greater, f1 minus f2, if f2 is greater, f2 minus f1. Because beat frequency is a positive quantity, right? So this is the frequency with which the amplitude oscillates. Okay, the amplitude is a variable and it oscillates with this frequency. So we have completed superposition, we have completed beat frequency, and with this we have also completely finished the waves revision. And so that will conclude this particular session for today. So I'll conclude this meeting, I'll end the meeting, right? So thanks a lot. I'll end the session now. Thank you. Bye all of you.